My name is Yuyang, and I'm a first-year master student in the University of Electrical Communications. I would like to talk about my graduation thesis, which is a design of a ground loop detectors for city road. Here's the outline of my presentation. First, I would like to talk about background and the theory of the ground loop detector, and I would like to introduce my hardware and software in design, the experiment and result. Finally, the conclusions and future work. Increasing road traffic activities might brought us several problems like traffic accident, traffic jam, energy waste, environment pollution. To facing on problems like this, it's important for us to know what is going on the road, like how many cars on the road, which direction they are heading to, and the speed of the vehicles. So my study focused on speed detection, which is an efficient way to handle traffic activities, especially on preventing us from traffic accidents. And what is the ground loop detector is? Ground loop detector is an isolated electrical conducting loop installed in the pavement. So it's a underground device which can detect vehicles passing or arriving at a certain point. Comparing to other car detectors like camera car detectors or the ultrasonic car detectors, it has several advantages like robust in variable weather conditions. Since it's blocked from outside world, and it has high accuracy and adjustable detection. And the third, it has a like perfect appearance, which is you can hardly notice it exists, shows in the graph. In the theory of the ground loop detectors, so when a vehicle passes over the loop, the vehicle decreases the loop unit inductance. The decreased inductance actuates the electronic unit sends a pulse on the traffic signal controller, signifying the passage or the presence of the vehicle. So using these two signals here, we can easily yield the speed of the car. But here comes the problem. Since we call it false trigger problem, since we cannot 100 make sure that the true signals from the loops comes from one car, come from this specific car. Then we proposed a design which runs the recognizing process before comparing using cross-correlation method. Here's a signal from loop A and here's loop B. Using this equation, which is a cross-correlation method, we can compute the similarity of the two signals. And you can see at this graph, and at the time point, at this time point, the signal A and signal B, similarity of the signal and signal B comes the maximum. So at this time, we can consider at this time as a processing time. And the hardware design. There are three parts in hardware network. First, the information source, which is vehicles. Second, the information collection unit, which includes the loop, the coupled oscillating circuit, and the AD transform. And third, the computing and the communication unit, which I chose the STM32 as our computing unit. And here's some supporting circuit, like crystal oscillator, JTAG, power source, reset circuit, serial communication. And I would like to introduce this part first, information collection unit. And using a capacitive 3-point circuit, it can gather, which is a classic circuit. It gathers signals from this point, T1. And gating switch is formed by Q3 and Q4. In this task, it's a multi-channel task. So we have to design a gating switch, which can make us possible to choose on which channel we are focused, using Q3 and Q4. And the communication unit, we use the RS485 as our communication chip. Signal communications are achieved through pin 1, 4, and pin 1, 4 are controlled by pin 3 and 2, S3 and 2. And pin 6 and 7, here's a clamping circuit, which can protect our communication chip. Here's the software design. This programming flowchart. We initialize session, frequency collecting, and if it's the first time we collect the frequency, then the frequency is set to be our baseline frequency, and set the sensitivity, compute the frequency change, and if the frequency change is over our threshold, then we can tell here's a car presence. So we let the LED up and output the signal to our host's computer, which is our computer. But the frequency of the coupled oscillate circuit is greatly affected by external factors, such as temperature, humidity, etc. We call it frequency drift. So setting a fixed reference frequency might affect the accuracy of the detection system. So we use the online frequency refresh algorithm in our system, which is this part. If the frequency change is not over our threshold, then we set the baseline, set this new frequency as our baseline frequency. Here's an experiment the result. Our simulation software is designed to visualize the performance of our system, and it's on the upper computer, and this software is on the lower computer, which is STM32. It's our host computer. As you can see in the graph, we set the given samples as a number of 3,500 sample data, and the current sampling frequency is set to be 0.01 megahertz. The co-spacing, which is the distance between two loops, are set to be 4 meters, and the waveform most similar point position here is at 1,829, and the calculated speed is 78.8 kilometers per hour. So, conclusions. We introduced our system structures and design principle, and adopted a cross correlation method to solve the false trigger problem. To surmount frequency drift, we proposed a baseline frequency refresh algorithm. Future work for the hardware, validate our hardware design and increasing detection accuracy. And for the software, add data analyze and data pre-process functions to the software. And I want to experiment my design in real environment someday. So that's it. Thank you.